So let's welcome first Clara, Fabiola, Oliva, Vice President of Data Analytics, AI, and Customer Insight, and also welcome Nicola Vizioli, Strategy and Data Analyst. They're coming to the floor to discuss team's journey to find the why behind customer behavior, find optimal interventions, and shape a data-driven future. Welcome, Clara and Nicola.
So, hello everyone. So, thank you very much for being here, for the opportunity, and for this event. So I'm Clara Oliva. I'm Vice President for Data Analytics, Artificial Intelligence, and Customer Insight in team, and I'm a board member of Olivetti. Team, I don't know if you know the company, is one of the biggest and also the historical telco company in Italy. And of course, as a big company, you can imagine how difficult is a transformation. And data transformation is a very difficult, a very big challenge for team. So I'm the responsible for choosing new technologies, of course, and artificial intelligence, tool set in order to support, both internal and external market purposes. Of course, artificial intelligence and data analytics are, the core to make the right decisions. And on one side, to create efficiency on operational process, and on the other side, to create new growth opportunity. It means that, of course, we need to understand better our customers, to talk with them in a different way, and to create new stream opportunities. But as I was saying, team has a very big story, and of course, transformation is a challenge. So the first thing that we had to work on was data strategy. So here in the slides, you can see some of the few core elements that were the starting point for us, of course, to make this difference. And we can start, of course, from the data framework, the data architecture. So having new technology, a new tool set, so having the opportunity to work in a new, environment, technological environment, of course, is one of the first steps that we need to do. And we started to do it, of course. Then data governance. So I know that it's very boring stuff, and it's made of data quality, data catalog, and so on. But, garbage in, garbage out. So the first thing that we need to do is to collect the right input data, to work on that, to work on quality, to work on processes. And here is the new, phase, because once that you have the right architecture, you have the right tool set, and you have the right information, the right data, of course, you need to start on process, organization, skills. So, again, big company challenge, we need to work on a data culture. We need to work on a different way of working and a different way of addressing our problems. And, of course, risk management. So, European Artificial Act, it's one of the new challenge for everyone. So we need to work, on the risk, addressing all the problems that artificial intelligence system and tools can create. So this is the first, layer. But starting from there, so we did a lot of work. So I have a team of 60 people working with me. They are data analysts, data scientists, machine learning engineers, artificial intelligence translators. It means, of course, that we need to support business units. And to do it, we need to create empowerment. We need to create this data culture. So we work on the day-by-day working. So it means that we created, here is just few, AI models that we were working on. But of course, it means that we need to support and to help them, even if it is a dashboard, it's important to help everyone to work on this side. And of course, what is important is the ambition. So the ambition, as I was saying, if we need to work on a data-centric environment, we need to understand and to empower AI systems, and also causal reasoning is one, of course, of this. And we need to work on better understand our customer. So the scope is, of course, customer care, marketing, and sales. So generating new, let's say, new contents and new personalized services. But on the other side, process automation, so efficiency is one of the main steps that we need to do. And also of course, all the CapEx optimization. As I was saying, causal reasoning is the target for us to understand better what we are doing and to make the right decision. And here is exactly what Nicola will explain to you. I will leave the floor to him, because of course, for us, decision is already part of our tech ecosystem. Thanks.
Good morning, everybody, and thank you, Clara, for your presentation, your introduction. So, in this session, I will try to sorry. As Clara said, I'm data scientist that now I'm working on this on our group. So I will try to explain to you our work on developing a causal inference framework that try to reduce customer churn in telecom industry. So during this session, I will try to walk you through our method, our strategy, and the valuable insights we gained combining causaLens Decision OS platform with our in-house causal inference platform and applications. So, as you know, telecom industry is a very competitive and saturated market. This is true, especially for Italy, where there are a lot of operators and where the customer prices are the lowest in Europe. So we understand that the cost of acquiring a new customer in this situation is much higher than retaining existing one. This is why we felt the need to understand what the behavior of our customer. Of course, so the question is, can we leverage on a non-core team service, in this case a TV service, to try to enhance customer retention and so reduce churn? As Clara said, in team we have been using machine learning models and also more complex deep learning models to try to predict churn. As you can see from some of the metrics I report in this slide, results are good but not optimal. Moreover, as you know, those machine learning models are inherently predictive. They can tell us who is likely to churn, but not why. Additionally, if you want to take some retention actions, for example, sending emails or discounts or offers, we eventually disrupt the patterns that those models have learned. So they became ever more ineffective. So we felt the need to switch from mere prediction to understanding causality and to try to estimate the real effect of our actions to take better decisions. So this study is focused on team-fixed database that team-fixed clients that gave consent to profiling. The dataset comprises of 3.3 million of instances we observed in one single month and more than 4,000 variables. So the richness of this dataset, of course, allowed us to delve deeper into better understanding customer behavior. But of course, it presented the challenge of dealing with a great search space. To overcome this issue, we used the solution proposed by causaLens decision S that aims to recursively merging pair of cluster of future. And it's essentially a hierarchical clustering based on variables greater than instances, and we got some good results. However, to have a better understanding of the cluster we are analyzing, we use a large language model to create a few clusters based on future description generated directly by the large language model. As you can see, I reported some of the prompt we use. Particularly, we use a LangChain library in Python to query the large language model. But also, we ask to the large language model to help us to identify some prior knowledge to put in the causal graph to obtain a more meaningful causal graph. As in this case, I reported some of the prompts. In particular, we asked to the large language model to identify clusters that are likely to be dependent from any other clusters, but we move further asking to identify direct causal relationship between clusters. Of course, being a sector expert, we were able to modify some suggestions, but in general, we found them quite accurate. So, as I said, we use this prior knowledge to run in decision as causaLens some causal discovery algorithms. In particular, we run PC, FCI, and Lingham algorithms. And finally, we choose the graph that better fits our expectations and eventually modifying manually some edges. So to evaluate this graph, this final graph, we use some independence tests. In particular, we test how many graphs obtained permuting the original nodes lie in the same Markov equivalence class than the original DAG. And since we found that our DAG is characteristic, is informative, we perform another test which aims to verify how many DAG permutations having as fewer local Markov condition violation than our DAG. As you can see, the graph we got from PC algorithm in this case has exceeded both of those tests, and so we don't reject the DAG. So the next step was to associate to the causal graph a structural causal model, assigning to each no-root node a functional form that can be, for example, an additive model of parents and observed noise. So in that way, we are able to perform a future relevance analysis that aims to identify which parent node has the greatest impact on the target variable. But more importantly, we are able to perform an intrinsic causal influence method that estimates the newly added information by a node in the causal path that was not inherited by parents. As you can see from this last model, some of the variance of the target variable remains unexplained. This can be due to some model inaccuracies, or maybe we don't consider all the relevant variables in our model, or maybe when we decide to use cluster instead of original variable, we lost some information. Anyway, results that we got are not trivial. Indeed, as you can see, our variable that we have chosen a priori as our possible treatment, that is our non-core TV offer, is indeed one of the most important in explaining target variable. So, in this case, it's safe to also switch from a model-based to a design-based identification. That is, we can also try to estimate the average treatment effect of this variable, of our treatment, even without relying anymore on the functional form of the structural causal model if we don't believe completely on them. What we need in this case is to deconfound the data. That is, indeed, we applied the 4 different causal inference methods to obtain the average treatment effect. all the methods, you see, agree on the same value that is, of course, much smaller than the one that we got with a naive estimation, that is computing a difference in means. But it's something that we are expecting, since now we are controlling for co-founders, and so we are eliminating their bias. But more interestingly, this causal approach gives us the possibility to identify clients that, or group of clients that we want to prioritize. Indeed, we use some the machine learning models like causal forest or other double machine learning models or double robust estimator to calculate the conditional average treatment effect. We use also some validation tests like a Gini curve and other uplift curve and R-scorer to select the best estimator for our data, in this case, the double robust estimator. At this point, we just need to fix a threshold value, or if we don't want to care about outliers, to select an interval to retrieve all the customers that are most likely to be affected by our treatment. And so we can focus only on them. Moreover, using always the same double robust estimator and some statistical tests, we were able to verify that a lot of those customers are indeed the oldest one in our database. So it's a result that quite surprised us, but it's very important because now we can easily access to them. So to sum up, combining causaLens decision S with our framework, causal inference framework, and also using some large language model causal capabilities, we were able to optimize the resources because now we can focus only on more sensitive clients, so we can save money and time. And of course, we can also maximize the impact, since now we can be pretty sure that unlike using machine learning models, predictive models, we are able to enhance customer retention. Finally, in this slide, I want to show you some other possible application of this framework that can be used in telecom industry. For example, we can select a variable that we need to target to upsell new services, or maybe select variable, identify variable that we need to consider if we want to reduce customer complaints, or even to find features that are the most related to customer patterns, so we can generate value through data monetization. And thank you for your attention.
Amazing. Thank you very much. We do have a couple of questions. We also have a couple of minutes, so hopefully we can get some answers for you. First question, do you run into situations of cyclic graphs, i.e. non-DAGs? How do you and Causal AI deal with these situations?
Yes, yes, there are sometimes we got some non-DAG graphs. Yes, we can, in causaLens, the decision has there is the possibility to choose the part of the graph that is not a DAG using a scorer. But we can also, for example, we can choose, we can examine also the graph and deciding with if the customer, if the user has a good knowledge of the problem, to decide to delete some edges, and so to select the part of the graph that, of course, to have a DAG. And so, but of course, causaLens has a scorer that can help us to decide which part of the DAG we have to consider, and so we can only work on this part of the graph.
One final question. How much uplift do you think you can get from using LLMs in causal discovery?
Yes, of course, we are as I said, sector experts. So maybe we were also able to build the cluster we use alone. But first of all, we have a lot of variables, in this case, more than 4,000 variables. So the LLM, first of all, help us to reduce the search space because also manually selecting all the variables to create a cluster is a big deal. But of course, using a large language model, we can speed up the process and then eventually we can modify what the LLM suggests to us. But in general, as I said, the LLM gave us a very good solution in building clusters and also prior knowledge to put in the causal discovery algorithm.
Amazing. Thank you very much.